Hello, everyone. Good afternoon, and welcome to another talk in the series of Valongo seminars. And I'm Luan Ghezi. I'm a professor here at Observatório do Valongo. And also, I want to thank the collaboration of Douglas and Ariana, and they helped me with the organization of these talks. And today we have a very special guest. We have Dr. Katie Bouman with us. And Katie is a Rosenberg Scholar and an assistant professor in computing and mathematical science and electrical engineering department at the California Institute of Technology. And before joining Caltech, she was a postdoctoral fellow in the Harvard-Smithsonian Center for Astrophysics. And she received her PhD in Computer Science and Artificial Intelligence Laboratory at MIT in EECS. And before going to MIT, she received her bachelor's degree in electrical engineering from the University of Michigan. The focus of her research is on using emerging computational methods to push the boundaries of interdisciplinary imaging, as you see very clearly during her talk. So Katie, thank you very much for accepting our invitation. It's a great pleasure to have you here on our talks. And whenever you're ready, feel free to start telling us more about this very exciting imaging of the black hole.
Thank you so much for the really kind introduction. Yeah, I'm really excited to have been invited and have a chance to talk with you, and hopefully be able to talk with you with questions and stuff after the talk. So today I'm going to talk a little bit of black holes and how we were able to take a picture of a black hole, and also kind of what are we doing going forward? What are some things that we're excited about? So, black holes are one of the most mysterious phenomena in the universe, and scientists have been studying them ever since they were first predicted from Einstein's theory of general relativity just over 100 years ago. And in particular, for decades, scientists have been studying this giant elliptical galaxy that's at the head of the Virgo constellation. This galaxy is called M87, and it's 55 million light years away from us, and it's really special because over 100 years ago, someone actually discovered this streak of light on the sky, which ended up being a galactic scale jet of plasma shooting out of the core of this galaxy and marking the spot of a supermassive black hole. And so over decades, scientists built better and better instruments to study the supermassive black hole predicted to be at the center. And then in April of 2017, we hooked up this Earth-sized telescope and took the data necessary to make the first picture of a black hole, which happened 2 years later after processing all that data. And so this black hole image was the result of a group of hundreds of scientists from all around the globe, coming from Europe, North and South America, Africa, Asia, that all came together to build this computational Earth-sized telescope that could take this image. And so today I want to tell you an abridged story of how we were able to capture a picture of a black hole. And I'm sure you know this from many kind of different points of view already. There's kind of many angles to the story. And so I'm going to tell you more about my primary contribution, how imaging was done and validated. And then at the end of the talk, I'm going to talk a little bit about techniques currently being developed in my group at Caltech to push the Event Horizon Telescope past its current limits to see environments that are still currently invisible to us. And in particular, we're developing machine learning methods to develop where we place the next telescopes in our Earth-size array. So the first question you might have is, how are we able to take a picture of a black hole that, by definition, doesn't let light escape, and so it should be unseeable, right? Well, the light around a black hole it doesn't follow straight lines. Because the black hole is curved, that means that because the space-time around a black hole is curved, lights don't go in complete orbits around the black hole. In fact, you can even make complete circles around the black hole. And so you have these photons that are flying around everywhere. They're heated to hundreds of billions of degrees. And so this causes those light photons flying around. Some of the photons fall into the black hole, but other ones just graze it, such that the net effect is essentially that the black hole casts a shadow on backdrop of hot material that's almost perfectly circular. And so this black hole shadow is a signature of the black hole's event horizon. And it's referred to as the black hole shadow because it's basically putting an imprint of the black hole on the backdrop of hot material. And if we were able to see it around a 1 millimeter wavelength, this is what we would kind of expect to be able to see. This is what computational scientists expect that the black hole kind of looks like if we could see with very, very high resolution. But even if we can see this imprint of the black hole, taking this image is still really difficult. And that's because this is an incredibly small ring. It's about 40 microarcseconds in size, which is about the same size as a grain of sand. But if that grain of sand is being viewed from all across the country. So if that grain of sand is in New York and I'm viewing it from here in California. And so even though this black hole is massive as far as black holes go, we can only barely see this booming jet that's on the sky. And when you kind of zoom down at it, you really have to get to around a 1 millimeter wavelength. Give me a second. My video is not working here. Could you give me 1 minute? My slides crashed. And so I need to, excuse me, sorry about this.
Hey, Katie, is it something local or is it in
local.
the broadcast?
Yeah, it crashed. 1 second.
Okay, good.
I'm sorry about this. It's the first time this has happened.
Don't worry. It's to build up the excitement to see the video.
Just wanted to make sure that all my videos don't stop playing. Yeah. Okay. So yeah, at long wavelengths, we actually can't.
I'm sorry. Can you please remove the there is a message from StreamYard. Can you slide that down the screen?
For this part?
Yeah. Perfect.
Okay.
Thank you. Go ahead.
Yeah,
Thank you.
So so what makes kind of seeing sorry, going back one slide. So because of the fact that this black hole is so small and we can only see it at a very particular wavelength, we need a very kind of special telescope in order to see it. So why is that? So at long wavelengths, gas actually shrouds the black hole and blocks all the light from within. And this is a simulation of what you would expect to see at around a 3 millimeter wavelength. And so you can't see that ring of light. But if you go to shorter and shorter wavelengths, the gas becomes optically thin, and we eventually, when you get around to a 1 millimeter wavelength, are able to see the event horizon. But even if you're able to see that ring, being able to take that picture is still incredibly small. And why it is because this is such a small ring, about 40 microarcseconds in size, as I said. And so you can only, it's about the same size as a grain of sand, but if that grain of sand is in New York and I'm viewing it from California. And so taking a picture of something that small is really hard. And that's because it all comes down to the limits of diffraction, which tell us the smallest things that we can see. So if you take your diffraction limit equation and you plug in the angular resolution of that we need to see that ring and the wavelength we need to pierce through and make the gas optically thin so we can see that ring of light, you can easily calculate that in order to take this picture, we would need to build a telescope 13 million meters in size, or essentially the size of the Earth. And if we could build an Earth-sized telescope, we could just start to make out the distinctive ring of light that's indicative of the black hole's event horizon. And so, although building a single dish telescope the size of the Earth obviously isn't possible, by joining telescopes located around the world, I've been working as part of an international collaboration called the Event Horizon Telescope Collaboration that built the first computational telescope the size of the Earth, capable of resolving structure on the scale of a black hole's event horizon for the first time. And so joining telescopes in this manner is called Very Long Baseline Interferometry, or VLBI. So how does this technique work? Well, we have telescopes from all across the world that are linked together through the precise timing of atomic clocks. And so at every one of these telescopes, we have teams of researchers that essentially record the light by freezing it, by recording petabytes of data that are time-stamped by these clocks. And then we bring them together and use our computers to act like the lens to make the picture. And so unlike within a camera, in the Event Horizon Telescope, we don't actually capture the picture in pixel space, but instead in its frequency space. So we essentially take measurements of the black hole image's Fourier transform. And if we covered the globe in telescopes, if we tiled it in telescopes, we would make all these spatial frequency measurements. We'd make all the measurements we need. But since we only have telescopes at a few locations, that means we only get a sparse number of measurements. And so it turns out for every 2 telescopes in our array, we obtain a single complex measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. And each of these measurements it's a complex number, so it's described by 2 numbers. Its amplitude and its phase, which it's good to remind yourself of this because it'll come in handy later. Okay, so in 2017, the Event Horizon Telescope observed with 8 different telescopes around the globe, but actually only 5 of those telescopes were able to see the black hole in M87, and we're at different locations. So that means that it would only be 5 choose 2, which is only 10 points that we'd have to make an image from, which is an incredibly small number of points. But luckily, as the Earth rotates, we obtain other new measurements. So since the projected baselines between telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in the spatial frequency plane. And we get these measurements by recording hundreds of terabytes of data at every telescope. So here you see my friend Lindy Blackburn posing with about a half a petabyte of data that we collected at the GMT telescope in Mexico. And we recorded so much data that we can't send it over the internet, and it's actually flown to a common location. And then at that common location, we use a special purpose supercomputer called a correlator to combine the precisely timed data. And then once this is done, it's passed on to a calibration stage, which finds weak signals hidden in the correlator output, and it tunes the parameters to extract a stronger signal. And so developing this pipeline unique for the EHT data, it was a very challenging kind of data set for this, was a huge task led by Lindy Blackburn, but with the help of many others. Without getting this data out, we would never be able to have made an image. So this is the first step of extracting this, you have very noisy signals in the telescopes, extracting this tiny signal within there that we can use to make images. But then how do we use this data to make it tell us an image? So at this point, we have this data, and we can kind of abstract away the astrophysics and look at it as a purely mathematical inverse problem. We have sparse data, and our challenge is to find the image that caused that. And if we were given measurements that covered the entire frequency plane, it would be a trivial task because in the case of no noise, you could just simply apply an inverse Fourier transform. But since we only see a few samples, that means that there's an infinite number of possible images that are perfectly consistent with the data that we measure. And on top of that, there's a quickly changing atmosphere above every telescope across the globe that causes our data to be really noisy. And so how does that noise enter our system? Well, the whole reason that we are able to do the radio interferometry in the first place is due to the fact that light from the black hole is going to travel to Earth for 55 million years, and then it's going to reach one telescope slightly before the other. And that slight time delay is key for extracting the 2D spatial frequency measurement that is used for image reconstruction. But when you have different atmospheres above each of the telescopes, then that causes an additional propagation delay, which leads to a random phase delay in each frequency measurement. And so now we've scrambled the phase because of this propagation delay. And similarly, this atmosphere also causes a random attenuation factor, which causes our absolute gain term. And so this error is very challenging because ideally we would measure this nice, beautiful Fourier component, the italicized V here on the right. In reality, we have a completely random phase error that scrambles our measurement, and oftentimes a pretty bad amplitude error as well. And so that's pretty terrible because at first glance, the measurement we've made has lost both the amplitude and phase information. And if you've lost, both of that, then what really do you have left to work with? But luckily, the measurement term has structure to it. And you notice that this measurement term is obtained by 2 telescopes. So every measurement comes from 2 telescopes, but these errors are site-based. So if we have a 3rd telescope, then the measurements that are formed with that 3rd telescope actually share some of the same corrupting terms, G2 and Phi2, with the first measurement. And so we can design algorithms to take advantage of this redundant corruption when solving for our images. And so to do that, we developed 2 different classes of imaging algorithms to tackle the problem. The first class of algorithms is based on a very standard method used in radio interferometry called clean with an iterative self-calibration loop. And this is a very traditional method that's used within the radio interferometry community. And so the big advantage here is it's vetted and people understand it. But the disadvantage is that sometimes it was developed for other kinds of telescopes, either that are working at longer wavelengths where you could do better calibration, or when you have a lot more telescopes to work with. And so when you're dealing with the challenging EHT data, it often needs a lot of guidance from a knowledgeable user. But even so, we were able to get it working with the hard work of a number of the people that I'm highlighting here. They were able to adapt this method to the EHT data. The second approach is a class of methods that we've been developing more recently, and this is something that I kind of more worked on this side of algorithms with Michael Johnson, Andrew Shale, and Kazu Akiyama. And in this method, we don't try to find an inverse function that takes us directly from the measurements to a picture, but instead we try to find a picture that both fits the measurements and is what is defined as likely through some sort of mathematical scoring of how good an image is. And so the disadvantage with these approaches is that you need to define what is a likely image, what is a good image, and that's going to always produce bias into what you recover in the end. But the huge advantage of these methods is that we can naturally incorporate all different kinds of errors that we expect to see on the Event Horizon Telescope data. And so, for instance, we can directly optimize with constraints that are insensitive to errors that I described earlier. And we typically do that through constraints known as closure quantities. So I'm not going to go through this in detail, but I just kind of want to give you a hint of what this is. So I talked about how the atmosphere causes these propagation delays, but in something called closure phase, so every measurement we make is a complex measurement from 2 telescopes. So if you multiply complex measurements, you're going to add their phases. And if you add up the phases from different measurements in a closed loop, actually that propagation delay cancels out completely and you're left with a term that is the same as if you had no atmosphere. Similarly, in a quantity called closure amplitudes, if you multiply and divide the measurements of 4 telescopes in a certain order, the gains cancel out perfectly and you're left with a term that is the same as if all the gains were perfectly unity. And so both of these closure quantities were actually determined a long time ago, but they're typically used for calibration purposes. But rather than just using them purely for calibration before the imaging is done, because the fact that our errors are so challenging and calibration is so hard, we actually incorporate these into the imaging process and do imaging assuming no calibration whatsoever. So the way that we do this is by modeling the forward system, our telescope as a function f of x, that returns these robust data products, the closure phase and closure amplitudes that we'd expect to see if the true image was actually x hat, and then we compare it to the actual noisy phase closure measurements y by computing something called the data likelihood. And this allows us to determine how consistent our proposed reconstruction is with the observed data while being invariant to the error that plagues the original measurements, like that atmospheric error. And through the data likelihood, we also incorporate other types of error that we expect to see on these measurements. But that still doesn't prevent us from having an infinite number of solutions. There's still an infinite number of solutions that will give you exactly the same y hat. So to deal with that, we have to incorporate what we call an image prior or regularizer that basically scores how reasonable each image is. And the way this does this is, of the images that are consistent with the measured data, some are more likely than others. And so we incorporate this to basically rank those images to determine what is the most likely, the best one. And so we incorporate this image prior, and this allows us to go from an infinite number of images to selecting one of them that is the most reasonable, even in the presence of all this kind of crazy noise. So this I'm just hand-wavily telling you about one kind of approach that we use to recover the image. But any method we come up with, whether it's this method I talked to you about, one of the more traditional methods, or maybe a fancy new machine learning method, they're always going to require that we inject some additional information into the problem about what images look like in order to deal with those infinite number of possible images, and that's always going to bias our final picture. And so we wouldn't want to accidentally have a preference for ring images and then be super excited we recovered a ring back in the end. So a big question we dealt with the M87 data is not just how do we reconstruct an image, but how do we make sure that what we are reconstructing with our imaging algorithms is real. And basically, we tackled this through a multi-step process that began years before we had even collected data of the M87 black hole. And that was the first step was to run synthetic data tests. So what we did is we had these challenges where we'd have a team of people simulate realistic data sets. So they would say, okay, let's say this is the actual true image in the sky, and let's generate these realistic data sets and make these data sets available without telling anyone what the true image is. And then people, blind to what the true image is, would make their best guess using their favorite algorithms at what this image is. Once we got these images, we then passed them off to a team of experts that we recruited to try to predict what the underlying structure was given these image reconstructions. And we did this test because it was essentially what was going to have to happen when we had to deal with our actual M87 data or the black hole data, where we didn't actually know what the underlying structure was. But unlike in the real data case, because this data is simulated, we could also evaluate at the end how well it matched up with the true image. So I want to show you a few examples of things we saw in these challenges to show you what we learned from them and how they helped us approach the actual black hole data. So here's one example. The true image is that was used to generate data is on the top, and it's blurred to the resolution of the interferometer right next to it. And on the bottom were 5 different submissions done by people who had no idea what the true image is. And you can see that although every image is different, they have slightly different features in them. Some have wispy structures where others don't. They all have this ring-like feature that is brighter on the left than the right. And so by looking at these different images that were made independent of one another and identifying what is similar and different among them, you can kind of gain confidence or in certain features and reject others as potentially artifacts. But we also wanted to make sure we could see something surprising in the center of the galaxy. We didn't want, in the center of, around the black hole. We didn't want to just make sure that we could recover rings. So we also threw in some random tests there too. So here was a submission for another challenge. And the reason I really like to show this example is because, clearly no one was expecting there to be a snowman in the center of the galaxy. Obviously, our imaging methods aren't either. But despite this, our algorithms were able to still see the structure that resembled Frosty the Snowman. And so this kind of test like this also gave us confidence that if there was something surprising there in this around the event horizon, we'd be able to see it. So based upon these synthetic data tests, we kind of developed how we were going to go and approach the actual M87 data. We wanted to avoid shared human bias like we had done in those imaging challenges I just talked to you about, in order to assess common features among independent reconstructions. And so to do that, we split about 40 people who worked on the imaging into 4 teams that span the Earth. And these 4 teams were actually not, when we first got the data, we went into our respective rooms and we didn't talk to each other at all about the imaging process for 7 weeks. So we worked in isolation, trying to make our best image from the data for 7 weeks. And then after 7 weeks, we all gathered together and we revealed the images to each other. And this is what we saw. So it was quite amazing to me. Just like in those imaging challenges I showed you, each picture is different. But despite that, they all reconstruct the same kind of basic structure, a ring of roughly 40 microarcseconds that's brighter on the bottom than the top. And so seeing these images was one of the happiest moments I had in the collaboration because it brought a whole other level of confidence to the images. that the fact that we got the same basic structure no matter the person or algorithm that we were using to reconstruct an image from that data. And I think we would have never achieved the same level of confidence in our results if we had not done this independent imaging test. But we still wanted to make sure, just because we hadn't imposed shared human bias doesn't mean we hadn't imposed some human bias, and that maybe we all wanted to see that ring structure. So we spent the next couple of months essentially trying to break our images. And that led to the next step, where we tried to objectively choose image parameters to remove humans from the loop as much as possible. And to do this, we developed 3 different imaging pipelines. These pipelines have their own individual knobs on them, hyperparameters that are usually tuned by a human user. But instead of having a human tune them, we wanted to instead search for the best set of knob settings that would recover different kinds of source structures and see how that affected our results of the M87 black hole. So for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky that had no hole in the center. And we found the best parameters to recover this disk shape. And then when transferring these exact parameters onto the M87 data, we found that our algorithm still required us to put a hole in the center, even though we had tried our hardest to find ones that would make a disk. And so by doing this simple training and testing procedure on many different kinds of underlying sources, we saw that our methods always preferred that ring shape. And that was true no matter the day we observed M87 on or the imaging code we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them to form an image that we showed the rest of the world last April. This ring of light surrounding the black hole, roughly 40 microarcseconds in size and brighter on the bottom than the top. And so, but at this point, we still weren't done. We still weren't sure that this was real. And so we went through a series of validation tests. I'm only going to briefly talk about one of them today, but you can look in our papers for additional tests and details that we did. So I just talked about how we selected one set of parameters, beta, that performed well on our synthetic data. This was the hyperparameters beta. But why should there really only be one set of parameters for our algorithms that work well that we should consider? In fact, by doing large parameter surveys, we found that there were often many parameters that actually performed reasonably well. So rather than just selecting one, we instead selected a threshold and chose all parameter settings that performed better than that threshold on synthetic data. And so we ran hundreds of thousands of simulations and found in one parameter survey about 1,500 parameters that we deemed acceptable based on synthetic tests on the data. And once we had these images, about 1,500, as I said, we could look across them for variations. So for instance, here is showing the standard deviation we obtained if you looked at the variations in the image reconstructions we did with different parameter settings. And you can see the standard deviation tells us there are some regions that we have less certainty in. So you see the bright knot regions along the bottom of the ring are areas that we don't have as much confidence in the exact flux value there. But if you look at the standard deviation and compare it to how bright that ring is, so looking at the fractional standard deviation, you see that we actually have a lot of confidence in that ring. That ring appears in basically all the images that we reconstructed that did well on synthetic data tests. But what you shouldn't believe is all that wispy structure on the outside. We do not have faith in that. So do not trust that. So, you know, overall, we made this nice image of a ring, but really, what have we learned from it? So one question that I get a lot, for instance, is, did we prove Einstein was right? And I think I like to give as the short answer, you know, no, we didn't prove he was right, but we also didn't prove he was wrong, which is also a big deal in itself too. And so to give you an idea of how we can use this image of the black hole to test our understanding of black holes and gravity, I'll just kind of walk you through how we can think about this, the ring size and compare it to the image that we have. So if you take a fixed size mass, you can calculate the radius that we need to compress that mass down to in order to get a black hole. So for a short scale black hole, this, you could calculate the short shell radius. For a non-spinning black hole, this would be its event horizon. But actually, what we expect to see is not the event horizon of the black hole, but actually the point at where photons are orbiting around that black hole. They're orbiting on unstable orbits, and so they fling off towards us, and they make this ring of light. But actually, because of the gravitational pull of the black hole, as they're coming towards us, they actually get lensed, and it becomes bigger. So for a non-spinning black hole, the diameter we would actually expect to see is 5.2 times its event horizon, or 5.2 times the short shell radius. And if you have a maximally spinning black hole, it gets pulled in a little bit, so that ring of light appears a bit smaller. And so this is the range of diameters between 4.8 and 5.2 times the short shell radius that we'd expect to see a bright ring of light about the size if the black hole is obeying canonical general relativity. But notice this is directly depending on the mass of the black hole. So for a smaller mass black hole, this ring actually becomes smaller. And that's interesting because from past measurements of M87's mass, it was actually very unclear what the mass was. So gas dynamics, people who studied gas dynamics, pointed us to about 3.5 billion solar masses as the prediction of how massive the black hole was. And stellar dynamics provided an upper limit, and they predicted about 6.5 billion solar masses. And so we wouldn't actually expect a ring, because stellar dynamics provide an upper limit, you wouldn't expect any ring bigger than that yellow one. Okay, but then we could ask ourselves, okay, how do we even turn this into a test of black holes themselves? Well, we can look at other unusual and exotic objects. For instance, wormholes also produce shadow features, but wormholes have a smaller shadow than a black hole for the same size mass. So here I'm showing the blue dotted line is the wormhole of shadow size from a wormhole for about a 6.5 billion solar mass wormhole. And also there are things called naked singularities or super spinning black holes that also produce shadows, but they would even be smaller than that, much smaller. And when you lay the Event Horizon Telescope on top of them all, you instantly rule out all these other kind of exotic possibilities, and you're left with a ring that matches nearly perfectly with the stellar dynamic measured black hole that's obeying canonical GR. So based upon this, we can see that it looks like the black hole is about 6.5 billion solar masses. But as I had talked about, this ring size, that ring that I'm saying is for a very particular orbit. So that's so you know, what exactly is the mass? So I'm saying roughly it's about 6.5 billion solar masses by doing this comparison of the size of the rings. But what exactly is that mass? That ring is that we calculated is only for the photon orbit, that place where photons are orbiting around the black hole. And if you look at a bunch of simulations, you'll notice that sometimes, actually a lot of the emission is from gas that's flowing outside of the photon orbit. So it's not the photon orbit itself. And so groups at Radboud, UIUC, Frankfurt, and Harvard all got together, and they made this huge simulation of, this huge library of simulations of black holes with different parameters. And by simulating these black holes and running them through our imaging algorithms and our feature extraction methods, we were able to calibrate for a true mass over diameter value of what the mass of that black hole is to the recovered diameter that we get out at the end. How do these two relate to each other? And by applying this calibration of the different ways that we could recover diameter, we were able to show that no matter the way that we recovered diameter of the black hole, whether it was through imaging and fitting rings on top of images we had reconstructed, by doing direct model fitting to the data, or by fitting simulations of black holes to the data, they all found that that the most likely mass of the black hole was about 6.5 billion solar masses, and that agreed really well with the stellar dynamic predicted mass that had been published earlier. And so I want to highlight some people here: Avery, Paul, Dom, Jason, and Ferial, that were really critical in doing this kind of evaluation of the mass of the black hole through this this model fitting and calibration. So this is just one of the many ways that we can learn about black holes and gravity by studying this image. But perhaps one of the amazing things is that we see is that by comparing the picture we made to simulations scientists have made for years, we find that the image we've taken is amazingly consistent with a number of these predictions. And on top of that all, I think I also want to highlight, when we started this all, the question was, would we see a ring, right? So we can analyze the asymmetries of the ring and exactly what the mass is, but I really think the biggest thing is we saw the ring. And that might seem obvious now, but that was the ultimate question when we started. Okay, but the simulations that I just showed you, they were all moving. So you might ask, is our recovered image of M87 also moving? And it turns out, in fact, it is. So another interesting thing is that we actually observed the M87 black hole over 4 nights that spanned a week. So we had 2 that were close to the beginning of the week and 2 that were close to the end of the week. And we independently imaged each of those data sets, and we could then take the images that we recovered from each day, string them together to form a movie, and play that movie. And if you play that movie, you'll notice that there's some variation, some evolution. So I'll play it for you here. It's really hard to see, so I'm going to play it for you again. You'll notice that the bright spot moves a little bit more from the left of the ring down to the bottom. So I'll play it again. Okay, so we don't have a good idea of what exactly is causing this variation, whether it's rotation of material or just material that's getting brighter or dimmer. And we're actually not even exactly sure where it appears in the image domain. But what we are very sure of is that the time variability exists. And that's because it appears in the raw measurements we take. I think it didn't play last time, actually. I didn't notice this. So let me play it one more time, this video. So it's a little hard to see. But what we really know is that it actually does appear in the measurements we take. And that's because if you look at the data we have taken of the black hole, and you look at it over the 4-day span, you'll notice that the data is very significantly different, which tells us that although we don't know exactly what has changed, we know something has evolved around the black hole. And actually getting a hold on a black hole's time variability is quite important for a number of reasons. It doesn't just give us a window into the dynamics around a black hole and hopefully an understanding of how these powerful jets, these galactic scale jets are forming, but it also helps us in mapping the space-time of the black hole that helps in our quest to constrain our prediction of general relativity even further. But actually, the black hole in M87 is not the only black hole we're interested in imaging. In the heart of our own Milky Way galaxy, 26,000 light years away from us, there's a cluster of stars. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped this path of stars for over decades. And by tracking the motions of the stars over time, astronomers have concluded that the only thing small and dense enough to cause this motion is actually a supermassive black hole. And in fact, this discovery led to the Nobel Prize in Physics, given just over a month ago or so, for the work of Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy, otherwise known as Sagittarius A star. So as awesome as M87 has been, it turns out that Sagittarius A star, or as we call it, Sag A star for short, might be able to help us better understand the remaining questions that we have around, and help us in our quest to constrain general relativity even more. And so Sag A star, though, is teeny tiny compared to, is teeny tiny compared to M87's black hole. And so that means the gas can orbit around it much more quickly. So whereas it takes 4 to 30 days for gas to make a complete orbit around M87, for Sag A star, gas makes a full orbit every 4 to 30 minutes. And so getting a handle, we would love to be able to reconstruct an entire video of the evolution of the gas every minute around the black hole. But if you thought recovering a static image from this sparse data was a challenging problem, recovering a full video of pixels with the same amount of data is much more challenging. And so as important as it is for us to continue pushing on algorithmic approaches to squeeze more out of the data, it's also important to realize that to extract more science, we also have to think about improving not just our algorithms that analyze the data, but also our instrument that collects the data to begin with. And so that's going to lead to the last part of my talk today on using machine learning, on new algorithms that we're developing for machine learning for optimized telescope design. So in 2017, we only observed with telescopes, as I've said, at 6 different locations. And making images was a really challenging problem with that few number of measurements, especially with how noisy they were. And although in the end we were very confident of the ring shape we got, it took us over a year to build that confidence. And so we've been building out our array in order to get more data so we can see more of the around M87, and adding telescopes in Greenland, France, Arizona, and the one I'm most excited about is that we recently got funding to add a telescope at Caltech's Owens Valley Radio Observatory, which I'm now at Caltech myself, and so I'm really excited that Caltech is becoming part of the telescope. But imagine what we could do if we could add 10 more. Well, not only could we reduce our uncertainty in M87, but maybe we could actually make a video of the gas falling into the black hole in the center of our own galaxy. And as I said, being able to do this would be a huge scientific gold mine. But before we just like plop down a bunch of telescopes, we have to be really careful. And that's because building a new telescope is expensive. It costs at least millions, but usually tens of millions of dollars in order to build a telescope. And so we really need to try to optimize, to try to find the locations that are going to give us the biggest bang for our buck. Where do we want to put telescopes that will get the most science out of them? And so how should we go about solving for the location of telescopes in our next generation array? Well, typically the design of the telescope array is idealized and considered independently from the image reconstruction problem. In fact, in the initial EHT, it was more about where are there telescopes rather than where should we place telescopes. But even when we place them, a lot of times people, ignore, don't consider the actual analysis that is going to go on afterwards. And so they make a lot of assumptions, for instance, ignoring nonlinearities in the system or complexities in the noise. But especially for problems where the data is so correlated, the noise is so challenging, it's really a huge missed opportunity to not consider these two components in our computational telescope together. And we really should be trying to optimize them jointly. And so how should we go about doing this? Well, if you rearrange the blocks in this diagram, you'll notice it looks very similar to what is called an autoencoder. And I'll explain what an autoencoder is in a second for those of you who are unfamiliar, but it looks like an autoencoder where the sensing system is the encoder that produces these measurements or codes, Y here, and the imaging algorithm is the decoder that recovers back the original image. And so deep encoders, where the encoder and decoder are neural networks, is often used for image compression. So you solve for the weights of a neural network that encodes, often in autoencoders, you solve for the weight of a neural network that encodes a picture in a small number of measurements at the same time as a network that decodes those measurements into an image. And by training the encoder and decoder together, you can often find ways to compress the data more so than you can if you just do hand-designed compression techniques. And so in the image reconstruction problem, because we just need, we can use an arbitrary mathematical function that takes us from the measurements to the output image. It just needs to be something that we can code up in the computer. And so we can use a neural network as a decoder. We can actually say, okay, let's put those EHT measurements in and hope it spits out a good image. But unlike in a generic encoder, sensing systems that we build must obey physical constraints. And so we can't just build, like, we can't learn a random mathematical function, a neural network, and then build that network using telescopes. So we actually need to be able to constrain our encoder to designs of things that we can actually build. And so we've been working on this problem of how do we add physical constraints into the encoder in order to learn an optimal telescope design simultaneously with an image reconstruction decoder. And my postdoc Hassan has been focusing on this work. And the approach that we proposed is to develop a physics-constrained encoder that we train with the decoder end to end. So let's zoom in to see how we do that. So from an input image Z here, we can define a forward model of the measurements that we'd expect to collect. And in this example, we pretend we have 3 possible telescopes to sample, color-coded blue, red, and green, and we indicate the measurements that come from these telescopes as colored dots. And these measurements can be complicated, nonlinear, correlated, noisy, whatever you want. And here we're showing all possible samples. And so we could pass all these samples off as collected measurements to our image reconstruction decoder. But if we did that, that would mean we'd actually have to build all of those telescopes 1, 2, and 3, in order to make those measurements. And so our goal is instead to choose among them to find the best to build. And to do that, we introduced what we call a sensor sampling distribution that characterizes the probability that we sample from a particular telescope. And we sample telescopes from this distribution, from this probability distribution, and then we mask out measurements that were not produced by those telescopes. So for instance, we sampled telescope 1 and 3, so only the red and blue dots remain. And every time we sample from this probability distribution, we sample different combinations of telescopes and obtain different observed measurements. And then these measurements are passed on to our decoder to recover an image back in the end. And so we can string all of these pieces together into a single differentiable neural network structure, actually. So we can write it as a differentiable optimization problem with trainable blocks highlighted here in red. So our ultimate goal here is to use the network to learn an optimal probability distribution of where to build telescopes. And we're learning this simultaneously with the decoder. So here is this is telling us where to build telescopes, and this is telling us how to make an image from those telescopes. And we do that by minimizing the loss, that tries to maximize the similarity between the input and output images. Another term in that loss tries to encourage sensor sparsity because we want to be able to make the best image with the smallest number of telescopes. And the third is that it encourages sampling diversity to make sure we have fully explored the space of possible designs. And then we learn the sensor sampling distribution parameters with the decoder during end-to-end training. So we optimize these two jointly. And we do this by searching over the parameters. I'll just kind of skim over this. We're modeling our image, our sensor sampling distribution as something called a binary fully connected Ising model. If you don't know what an Ising model is, that's okay. It's just a joint distribution over on and off state. So we want to say, given that it's given a telescope is on, how likely is it that all the other kind of telescopes are on? And it's parameterized, but 2 types of parameters. The first one we call site activity, which is basically how important it is to turn on any one particular site. And the second is site correlations, that tells you if you have one site on, how important is it for another telescope to be on, or do you want that telescope to be off? And why would you want to turn a telescope off? Well, just to conserve resources. So we want to be able to find the best image with the smallest number of telescopes. And so we search for the model parameters theta here of what that produces the best images. And so here is an example of a telescope distribution that we have learned using this approach. The Ising model parameter theta jj, again, quantify the activity or the importance of every telescope. And the model parameter theta jk on the right quantify the correlations between pairs of telescopes, where red represents positive correlations and blue represents negative correlations. And from these recovered distributions, we can see some patterns that we expect to see. For instance, in the case of uncorrelated noise, in many cases, co-located telescopes are heavily penalized from sampling together. And that makes sense because in the case of simple noise, if you have two telescopes that are at the same location, they're going to make the same measurement. And so why would you want to make that measurement twice? But my favorite is not just the things we'd expect to see, but the things we don't know what we expect. So for instance, by changing the type of noise we train with, we can also see how this affects our result. For instance, this is a result with purely Gaussian thermal noise included on the telescope measurements. But when we include difficult atmospheric phase air that plagues our measurements by scrambling our data, the array preferences actually change fairly drastically. And so notice that when I flip back and forth, the correlations have changed. And so we find that this tells us about structures in the array preferences, in the geometry of the array, that are preferred in the case of challenging atmospheric noise. And so this approach allows us to deal with complicated and correlated noise that is not typically something people can consider analytically. And this shows us that it actually is quite important in optimizing the telescope to consider the particular type, the intricacies of the forward model that are being used to generate data. And so I'm really excited to be able to handle these much more complicated models now, learn from them, and use techniques like this to build out the next generation of the Event Horizon Telescope. And so using this approach, we're starting to understand where we want to be placing our next ground-based telescopes to reveal more of the unseen. And I'm also excited we may be applying it to a variety of other scenarios, including even the optimal placement of telescopes in space. And so, I'm very excited here that we're soon going to be using these approaches like this to recover even more than what we have seen already. So to close, it's clear that we have learned a lot from this image of the black hole in M87 already. But what I hope I got across in the talk today is really we're just at the beginning. And now that we have this extreme laboratory of gravity, we're already thinking towards the futures and ways that we can improve our instruments and algorithms, improve them jointly to learn even more. And so hopefully one day we won't just show you a static image of a black hole, but a movie of a black hole as gas is slowly falling towards its event horizon. And so with that, thank you, and I'm happy to take any questions. Sorry for the technical difficulties, and hopefully I didn't go too far over.
Okay, Katie, thank you very much for this fantastic talk. It was really, really exciting to learn all the details on how you guys got the first image of a black hole and all the exciting prospects for the near future. So it was a fantastic talk. We are completely overwhelmed with comments and questions here on the chat. People were very excited too about the talk. So
excited to answer some questions.
Great. I'm glad you said this because there are a lot of them. So let's start here with, okay, we have this question here from Carolina. So she thanks you for the amazing presentation, and she wants to know a little bit more about the details for why the need for analyzing radio data in Fourier space instead of the real space itself.
Yeah, so great question. So the reason that we do it this way is because this is what we're able to get. If we could actually get a picture itself of the image in actual space coordinates, then in the spatial domain, that would be better. But to do that, we'd actually have to build a telescope that is the size of the entire Earth in order to take a picture of the resolution we need. And so because we can't do that, we instead put telescopes around the globe and use this partial information to recover the image. And it just turns out, you can see, like, if you do some simple equations, well, it's not actually that simple, but much smarter people many years ago did these equations and found that actually if you correlate the information that comes from two telescopes, if you have a time series of the data that's coming in, so the light from the black hole is going to reach each of the telescopes, and they're going to be slightly time shifted from each other. And that time shift actually results in something that is related to kind of the Fourier transform of the image. And it's a little hard to explain without drawing, but you can see that if you basically had a point source, actually, I think it's just very hard to explain without drawing. It'll take me too long. But basically, it turns out that if you take two signals and you correlate and time average it, it drops out that it is related to the frequency, spatial frequency of the image related to the projected baseline between the telescopes. So if you put telescopes that are close together, these actually are going to get broad structure in the image. And so to get the fine detail, you need to see that ring. You actually have to put your telescopes as far apart as possible. And so the direction tells you about the direction of the Fourier component, and the distance between them tells you about the frequency component of the image that you're probing. So good question.
Okay, thanks. So you can see some comments here that you are an inspiration to young women, young scientists.
Thank you.
Oh, people and myself included were crazy about the snowman image. That was really cool. So
I tricked people with that one. That was my doing. I think that, so I told you we gave it to this team of analysts afterwards. So we did the reconstruction and everything, and then we passed it on to the team of experts. And the team of experts, they were like, well, maybe it's a binary black hole system or something. So, maybe we wouldn't be so good at analyzing the actual physics behind what's going on, but at least we recovered the snowman structure.
That was really, really cool. So I have some questions here specifically about women in science, but I would leave them for us to close with those, because they are, I think they're longer. So let's go with this one. So Karim asks, how much of this image analysis approach is specific to the EHT? Mm-hmm. So could we be getting more information from other interferometers? And she continues on to say, she wonders how different is to the kind of work that people at ALMA does.
Yeah. So actually, we developed methods for years before we even had data. And so to test those methods, we actually ran them on other data sets, for instance, ALMA data, publicly available ALMA data, or also the very long baseline array, VLBA data. So other kinds of interferometric, radio interferometric data sets that we could apply these techniques on. I would say that it's a little bit of both. One is that, yes, these techniques are definitely applicable to those other radio telescopes, interferometers, connected element ones too. But the where I would say it's harder is that we really design these algorithms with the EHT in mind. And so the EHT has more of a challenge with the number of telescopes. There's more noise in the data. For instance, the atmospheric air is not something that you can calibrate out in the EHT, where you can. In most the ALMA data, it's calibrated out. And so I would say they don't have as big of an advantage compared to the traditional clean techniques currently in those for those telescopes, although they do have an advantage. And I would love to be able to scale them up. So one disadvantage is those data sets have not the VLBA one as much, but the ALMA one has so much data, right, that it becomes computationally expensive to run these methods. And so we need to think about ways of scaling these methods up. So although I do not work with ALMA, I am at Caltech a part of this new telescope that is hopefully being built, called the DSA 2000, and it has the opposite problem of the EHT, is that they have 2,000 telescope dishes they want to build. And so there's so much data that it's 5 terabits of data a second that comes in. And so you can't run these optimization-based techniques. And so we have to come up with new ways that also incorporate the knowledge that we incorporated into the EHT techniques, but in a manner that's much more computationally efficient. So this is I think the ideas that we've had are applicable to across many types of telescopes, but you kind of have to consider the challenges of every telescope in tweaking these ideas to work best for them.
Okay, thanks. So next question from Thiago. He was looking at the snowman, and he had the impression that different methods were more sensitive to different angular frequency. Was that the case?
Yeah, so I talked about how we had these different kinds of approaches that we developed, and that was really important. And I think, at the beginning, I think it was hard to convince people how important that was. It was like, well, all we need is one algorithm. But as I tried to get across in the talk, each algorithm has its different biases, and it's hard to quantify that. And so it was important that we had different kinds of techniques that had different biases, and to see that we got the same structure out of them. So the images that had lower angular resolution were more of those traditional techniques they just what they do with the clean techniques, it actually solves for a bunch of point sources that fits the data, and then it blurs them together. And so this has some intrinsic highest resolution, and that you can't get past, I guess, because of the procedure that they do. The techniques that I talked more about, these like regularized maximum likelihood techniques, that you're solving an optimization problem for the exact pixels in the image, usually are a bit higher resolution. I would say you need to be careful with them because they'll start super resolving too. And although I think there are studies, though we have some papers that show that we can get pretty confidently some level of super resolution, you need to be really careful when you're trying to super resolve too much. So that's why, I think it's important that we have the traditional methods too, to keep us, grounded in what is what can we really believe in these images. But good observation.
Okay, thanks. So we had some questions about Sagittarius A-star, but you covered that during your talk. But this one, of course, I don't know if you can say that, but do you want to make any bets on how soon?
I can't give any timelines or anything, but I can say that we're working really hard on it. But it's very challenging compared to M87. So I talked very briefly about one reason it's challenging. Actually, maybe I can expand on it a little bit more. So M87, as I talked, is 6.5 billion solar masses. It's this massive, enormous black hole. And Sagittarius A-star is 4 million, which is huge too, but compared to 6.5, it's pretty small, right? But because Sagittarius A-star is so much closer to us, it appears about the same size in the sky. So although it appeared the ring is about the same size, the sizes of the event horizon and is much different. And so that means the absolute sizes. And so that means the gas is going to spin around Sag A-star much faster. And so whereas it takes 4 to 30 days for the gas to make a complete orbit around M87, it takes 4 to 30 minutes. And remember, we're collecting data over the course of the night. That means every measurement we make with the Event Horizon Telescope is coming from a different sample of this black hole movie, right? And so we no longer can throw all the data into a big pot and say, hey, tell me what image fit that data. We now have to consider every measurement we make is coming from a different image. And so that's just a much more challenging problem. That, I think, is the biggest challenge, but there's other things too, like between us and the black hole in the center of the Milky Way, there's the interstellar medium that causes scattering, and this makes it look like we're looking at the black hole through a frosted window. And so we have to, how do we remove that effect as well? These are other things. And so we're hard at work at this. I talked about making movies. That is like our ultimate goal. It probably will not be the first thing that we do. We'll probably try to account for time variability in some way and give some sort of average structure. But yeah, I can't give timelines, but we're working hard at it. Last week was our collaboration meeting, actually, where we're, updating everyone on our progress and everything. So it's an exciting time.
Cool. Good luck with that. Hopefully, we'll be able to invite you next year or the following years, whenever we have the image of the Sagittarius A-star, so you can update that to us. So thanks. Oh, this is a nice comment here. So Viviane really liked your examples, your presentation are very,
Thank you.
You know how to explain everything really well, and she really admires you. We'll come back to a few questions later here. Okay, so we have
hard work for many people that their ideas, filter into these talks.
Yeah, that's important to highlight the huge collaboration work. In fact, we have a question about about this, we are going. Oh, okay, we can do this right now. So we have a question from Iana. She asks how it was working at such a big collaboration with so many different people and physicists, astronomers. How was that?
Yeah, no, it was absolutely an amazing experience. So when I first started on the project, I started, how many years ago was it? Like 7 years ago or so on the project. I started as a grad student, and I was coming from actually a computer science kind of department. So I didn't have any knowledge in the astrophysics side of things, but I thought this was a really cool project. And so I started working on it. And initially, I was kind of working on it alone. I was like, read the textbooks, try to understand the equations, and code up a little algorithm. And pretty soon, I realized that this was not going to work. There was like no chance that anything I do would be at all impactful if just like kind of working alone. And so after that, I met some new postdocs and students who had just recently started on the project, a little about the same time as me, and this is when things really took off, because we became, I would go to Harvard. They worked at Harvard, and I worked at MIT, and I would go and meet up with them once or twice a week and work with them and slowly learn from them about the astrophysics side of the problem, and they'd learn from me more the imaging and computational sides of the problem, and this is really what made it a success. It was a lot of fun. We'd have like these hack days that we'd put together, because we learned like hackathons were actually very productive and fun and stuff. And, these people were amazing colleagues and turned into amazing friends and stuff. And so it was quite, I think, it definitely wouldn't have been possible without bringing together lots of different people with lots of different backgrounds to make it possible. I will say, like, going to large collaborations, I'm really happy that we did it. And I think it was essential, that was required for the kinds of result that to get the image, and to also, like, even once the data was collected, to get the result, to have the same level of confidence and rigor in the results that we had. It was essential that we had a lot of people contributing to that. But it is a challenge working with a huge collaboration like this. It's not, if you think writing a paper with a few authors is difficult, writing a paper with 200 authors, everyone who is all very highly opinionated, right, is even more difficult. So it's not something that's like, adding people is not easy. It's often harder, but it's worth it in the end. So you kind of have to stick with it and try to learn. And this is something we're learning in our own collaboration, of how do we deal with this, because it's not something that as academics it's normal. It's becoming more normal, but we're learning how to make it so that we can all work together and in a healthy way and be in a productive way. So it's something, yeah. Anyway, I just want to say both sides of the coin. It's something that, as science is pushing the boundaries even more, this is going to become more typical, that you need to have these collaborations to get out these results. And they're really rewarding, amazing experiences, amazing friends that you make. But it's also, there are challenges with it too, that we need to learn how to, in the science community, how to deal with.
Thanks. That was actually a great summary. Thank you very much. This certainly is very helpful for young scientists who are watching this talk. Thank you very much. Moving on to the next talk. How about stellar mass black holes? Are there some perspectives on using EHC to studying them, or in the future?
So stellar mass black holes are going to be too small for us to see. Also, they're not bright enough, I think, for us to be able to see. So I don't think that there are prospects of us to be able to image stellar mass black holes. So as I talked about, we at the very end, very briefly, I mentioned, we're also thinking about going to space. What space will allow us to do is have longer baselines. So we're restricted on Earth, right, to the longest baselines that we can have, and that restricts the resolution, because remember, as I said, the spatial resolution that you get is related to the baseline between the telescopes. So you go out to space, you can have really long baselines, higher resolution, but even if you went out to really high, even if it was bright enough that we would be able to detect it, we wouldn't, I don't think, be able to make images, because we wouldn't have enough space baselines. It would be just far too expensive for us to be able to put enough space baselines at that resolution to make an image. Yeah. So but one thing that we do talk about with, not super seriously yet, but we have talked with people. So one interesting thing is like the LIGO collaboration, right? And they are not imaging, they are detecting stellar mass black holes. But there's the LISA, which is potentially in the future that would detect supermassive black hole mergers. So there are talks of, would it be possible to at least image these sources at high resolution, not necessarily seeing the event horizons, but seeing the jets coming off of them and things like this. So that's kind of one direction where those collaborations could, there might be some complementary nature to them. And then also there's this other collaboration called the gravity collaboration, which is a interferometer, but in the infrared, and they've imaged like hot spots moving around Sagittarius A star. So that's another area. I know I'm getting it. I know this is not the question, but as long as I'm talking about other kind of connections with other collaborations, that's another direction of how we can collaborate with another kind of telescope to see other things that we don't currently see. And as far as exoplanets, I think that there are some interest in using optical interferometers and near infrared interferometers for exoplanets, although I'm not super familiar with it, but not for the Event Horizon Telescope.
Okay, thanks. So two more questions. So one very quick one. So what are the next targets besides M87, Sagittarius A? Do you think that there might be a survey in the future?
Yeah, so good question. So the two black holes that we know of on the sky that are biggest are M87 and Sagittarius A star. And those are the two that we expect to be able to see with the Earth-sized baselines. So to see black holes at other black holes that would be smaller in the sky, we'd have to go to those space baselines. And that is something that we are interested in doing. It will just not be something, I think it will take we're in the early stages of it, and doing something like that takes decades. But going to space, even more closer, like even orbits that are not too far out there, would bring into view a few other black holes, what we believe with our current mass estimates of those black holes. Other than event horizon scale structure, we also do image currently other sources with the Event Horizon Telescope. So we look at other active galactic nuclei and image the jets that are coming off of them at different resolutions than we have been able to do in the past. So for instance, actually with the M8, I didn't talk about this in the talk, but with the M87 image, we also imaged the Blazar 3C279. And what this allowed us to do was, when we independently imaged that structure, we could recover calibration parameters from it and check that our calibrations match that we had recovered with the M87 images. And so we used it almost like a calibrator, but in itself, it's actually a science target. So then we published a paper specifically on 3C279 and its evolution over the course of a few days in a follow-up paper. So you can take a look at that. And there are other kind of AGN that are in the works that we're imaging and publishing science papers on. And then as far as survey, I think it will be, I don't think it's I feel like there's very difference between a pointing telescope and a survey telescope. It's never going to be, I think, a survey telescope that it's always imaging. It takes too many resources, but it is something that we're hoping it could go on, like something where we don't have to spend, like I went to Mexico for every year for 2 weeks, to image. And that's a lot of time. And I'm just one person, right? And so it's a lot of effort to even do one observation. So eventually in the future, we'd like to have it be remote observing. And so you can observe throughout the year without just having so many personnel devoted to that.
Okay, Katie, thanks. So as we are close to our time limit, so there were lots of requests for these questions, and I'm putting here our representative one. So guys, I'm really sorry. We're completely overwhelmed with your comments and questions. Thank you very much for that. And unfortunately, we'll not be able to go through all of them. I'm really sorry about this, but I would like to end with this one, and we have lots of similar ones, Katie. So lots of people are saying that you are a huge inspiration, and of course you are. You're young scientists working really hard within a collaboration on amazing results. So congratulations for that on behalf of Valongo Observatory. We also admire your work. But can you talk a little bit about? So you are a role model now for young women scientists. So can you give young scientists, especially girls, any advice on how is it to work on this area, being a woman, and any other things that you might want to add to the young women that are watching us?
Yeah, sure. So first, I'm just incredibly honored, that people, the kind things that people are saying, and I never ever thought of myself as a role model, and so it's just I'm so happy that at least some people are gaining some inspiration from the work that our group has done, and hopefully want to go into the sciences more and are inspired, especially young girls and boys. But yeah, as far as being a woman, I think that there's always ups and downs to everybody, and everyone has their different challenges that they're dealing with. And so, as far as being a woman, I've been I definitely, everyone has their downs, as I said, but I've also been incredibly fortunate to have a number of really wonderful mentors who have supported me, a family that supported me and pushed me into the sciences and engineering from a young age. And I think that that is, I'm so grateful of that. I think that there are two, tips that I've had based upon my own experiences. One is that sometimes you get into situations where you aren't dealing with people who are very supportive of you. And in those cases, I've had situations where I had really cool projects that I was working on and that I really love these projects, but it was just a toxic situation working with people who didn't treat me, with much respect. And in these cases, in the end, it took me a while to realize it, but just it's work, if you're around people that you don't enjoy being around, then you're not going to do good work either. So make sure that not only you love the work, but you love the people, that it's a balance, but make sure that you surround yourself with people that challenge and support you, and you're not in an environment where you're always just fighting for survival. And so get out of those situations if you're in those situations. I know that afterwards I was much happier after doing that. And then two is, I think that I think a lot of women deal with this. I mean, I think it took me a while to admit this was, but for me, but I hope, yeah, anyway, a lot of people deal with this imposter syndrome, right? Where you think, oh, I just got here due to luck, and I really don't deserve it, and I'm not as smart as all these other people around. And I think that people can do things to hold you back, but really in the end, I think who holds yourself back the most can be yourself. And so, a lot of times if I start believing these things, even if, not necessarily even what people are telling me, but just what my head is telling me, right, then I'll stop working on and I won't do my best work because I just don't think I deserve it or something like this. And I think I always have to just keep reminding myself that that's not true. Just I can be my own worst enemy. And so don't let yourself be your own worst enemy. Don't let people tell you that you can't do anything, you can't work on a project that you're really excited about. Just find the things you're most excited about and work on them, because when you're excited about them and you enjoy the environment that you're in, you do your best work and you'll do things that you'll amaze yourself. And and I think that you just have to continue to remind yourself of that. So I think those are my tips. But yeah, just keep pushing forward, I would say.
That's amazing, Katie. Thank you very much. So there is lots of love going on in the chat. So I'll just sample a few messages here for you. So Ricardo says great work and thanks you. So Ana Clara says that's one of the best talks she's ever seen. Mariana says that's truly amazing. You're such an inspiration for young women. So there are lots of these. I encourage you to go to the chat later to see lots of these messages. So fantastic talk. Congratulations, Katie.
Thank you for the kind messages. And if anyone has burning questions, feel free to email me and I'll try to get to them.
And so as we now approach to the end, I would really like to thank you very much again for being here with us. It was a fantastic talk, and it was really a great pleasure to have you here and listening to the fantastic achievements that both you and the people at Event Horizon Collaboration achieved. So do you have anything that you want to add before we close the broadcast?
Just thank you so much for giving me the opportunity to talk with you today. And I've loved hearing your questions. And as I said, if you have any burning questions, just feel free to email me and be happy to get back to you. Yeah.
Okay, Katie, thank you very much. And with this, we complete our seminars in 2020 with this beautiful talk from Katie. I hope you liked it. I hope you have a great end of the year. Please stay safe, and we'll be back in January with new talks. So stay tuned. See you in January.
Happy
Bye-bye,
holidays,
everyone.
Bye.
Happy holidays. Bye-bye.